So let's continue our discussion on the introduction to number theory. I'm going to start by defining a new concept. So for integers a and b and a natural number m, we say a is congruent to b modulo m if m divides a minus b, or equivalently m divides b minus a. So of course, if m divides a minus b, that means there's some integer k such that ab equals km. Well then, of course, m would divide b minus a with the integer minus k, right? So they're the same condition, just two ways of writing it. We also write a is congruent to b mod m, like this. And you can think of this as a minus b percent m equals 0. Now we'll eventually prove this later, but this is just another way of thinking about it, for those of you that know about the modulus operator from programming. Okay, so let's prove this right now. So proposition for a and b and z, and m and n, with a congruent to b mod m, we have that a and b have the same remainder upon division by m. Okay, so let's prove this. So if we have that a is congruent to b mod m, we can interpret this as m divides the quantity b minus a. We can say a minus b or b minus a, either way. Now if m divides this quantity, that means there exists an integer k such that b minus a equals mk. Now, the division algorithm tells us that there exist unique integers q and r. Oops, kind of messed up that r. Integers such that 0 is less than or equal to r, which is strictly less than m, and a is equal to qm plus r. And applying the division algorithm again, it means there exists unique integers q prime and r prime such that 0 is less than or equal to r prime, which is strictly less than m, and we have b is equal to q prime m plus r prime. Actually, I'm going to move this one back up there just to make things make a little bit more sense. Division alg. Okay, so these things both follow by the division algorithm. If you recall, the division algorithm was that for any two integers with the second integer non-zero, I have that there exists unique q and r, which we might call the quotient and remainder, such that 0 is between r and d, and a is equal to qd plus r. Right. Now, in this case, we don't need the absolute values around the m because we know m is a natural number. Okay, so let's compare two ways to write b minus a. So we're going to consider the quantity b minus a. Well, I'm going to cheat a little bit. I'm going to leave a little bit of space here and write my first way to express b minus a is k times m. Right, we got that up here. Yeah, or mk, either way. And the second way is going to be using these two expressions. So I've got qm plus r for, q prime m plus r prime for b minus qm plus r for a. Right, so I use this for a and this for b. Now if I rewrite this by factoring out my m, I'm going to get m times the quantity q prime minus q plus r prime minus r. That's what's left over. Well, this is a multiple of m, and this is a multiple of m, and these are two numbers that are between 0 and m, excluding m. Okay? So, what's that mean? Well, I can move things around a little bit. Let's move all the m factors to the left-hand side, and I've got m times k minus q prime plus q equals r minus r prime. But both of these are in the set 0 up to m, excluding m, which means they have to equal each other, because the only multiple of m that I can get with a difference of two numbers out of here is m times 0. All right? So this last step's a little bit tricky, right? Because it involves making sort of a leap of logic here. So this must be, each of these are between 0 and m, and we know that r minus r is a multiple of m, so it has to be m times something, but I've got, the difference of two things that are strictly less than m and non-negative, well, they must be equal then. Okay? So this proof is a little hairy, so I'm not going to require you to know the proof, but I am going to require you to know the statement of this proposition. Just wanted to kind of air out those definitions a little bit. So this proof, I think, is pretty straightforward right up until this last little bit here, and I don't want to have you all trying to fight through that too much. Let's do a couple of quick examples, get kind of the taste out of our mouth of that thing. Notice that 14 is congruent to 2 modulo 6. And why is that? Well, if I divide 14 by 6, I'm going to get a remainder of 2. And if I divide 2 by 6, of course, I'll also get a remainder of 2. You can also see that 14 minus 2 equals 12. And we know that 6 divides 12. Okay, let's do another quick example. We've got that 9,475 is congruent to 5 mod 10. Now, I didn't have to do a whole bunch of division or whatever. I just know that the last digit is going to be what this is equivalent to mod 10, right? So if I were to divide 9,475 by 10, I would get whatever, remainder 5. And that's all I care about, is that remainder. All right. I'm fully confident we could write this out, but that's not the focus of this lecture. So the next big thing I want to do is Theorem 5. And Theorem 5, you are responsible for part 1 of Theorem. Well, you're responsible to know Theorem 5. You're responsible to know the proof of part 1, and the proof of part 2 is pretty similar, but it has it has just a little bit of a trick in it, so I'm not going to hold you responsible for the proof of part 2. I mentioned that in the previous video. So we're going to let m be a natural number, and we're going to let a, b, c, and d be integers, with a congruent to b mod m, and, well, that was just terrible, c congruent to d mod m. Then we have the following two conclusions. We have that a plus c is congruent to b plus d mod m, and we have that ac is congruent to bd mod m. All right, now let's prove the first part. So the first part, what I'm looking to show is that this minus this is a multiple of m. That's kind of the goal, right? And the second part, what I'm looking to show is that this minus this is a multiple of m. So in order to do that, I'm going to write out what these two things mean by unpacking the definitions, kind of like what I did in the previous example. Sorry, not the previous example, in the previous proof. So A congruent to B mod m means that m divides the quantity A minus B. It also means it divides the quantity B minus A. Either way is fine. We're just going to write it how we see fit. But m divides a quantity means that quantity, A minus B in this case, can be written as an integer, km. So there exists an integer k such that A minus B equals km. Now we're going to run the same game with this equivalence here. C congruent to D mod m implies that m divides the difference C minus D, which means there exists an integer k such that C minus D, we've already used k, we're going to use L now. And it's again a cursive L, just because if I use a normal print L, then it might be rough, and I don't like to mix capitals and lower cases if I can avoid it. So exists an integer L such that C minus D is equal to LM. Okay, now for part 1, we're going to consider the quantity this minus that. So that's going to be A plus C minus B plus D, right? So I've got A plus C minus B plus D. And if I rearrange this, if I distribute this minus sign, I'm going to get A plus C minus B minus D, which now I can shuffle the order of these things, and I get A minus B plus C minus D. Now, some people get a little uneasy because they're like, wait, you can't change the order if there's a subtraction involved. But I'm just changing the order that I subtract things. So I'm not making C minus B into B minus C. I'm not changing it like that. But so now the B is still negative here, the D is still negative here. Now we notice that these are precisely the quantities that we already have a handle of. So A minus B is Km, and C minus D is Lm. So this is m times the quantity k plus L. But guess what? K plus L is going to be an integer, which means m divides the quantity A minus B plus C minus D. Sorry. It does. But that means m divides this quantity, which is equal to this quantity. So what we really wanted to show is that m divides the quantity A plus C minus the quantity B plus D. And this is precisely the definition of A plus C is congruent to B plus D mod m. Okay, so this I think is relatively straightforward. Again, let me go through it. I know I sort of stumbled over some of the symbols here, but the main idea is I need to unfold this and I need to unfold this. So I unfold this by writing A congruent to B mod m is m divides A minus B, which means there exists an integer k such that A minus B equals km. To unfold this, I say C congruent to D mod m implies m divides C minus D, which is the same as saying there exists an integer L such that C minus D is Lm. Now this is just setup for both of these parts. Specifically to prove part 1, I need to consider the quantity that's involved with this equivalence here, which is going to be left side minus right side. Now you can do left side minus right side or right side minus left side, it doesn't matter, but we should stay consistent, so I'm doing left side minus right side, and I get A plus C minus B plus D. I rewrite it using some arithmetic, and then I get A minus B, which I know something about, plus C minus D, which I know something about. So I substitute in for these, and I factor out an m, getting m times an integer. If this is equal to m times an integer, that means this is a multiple of m, which means m divides this. But m divides this means that this thing is congruent to this thing mod m. So A plus C is congruent to B plus D mod m. All right, and if you need to, you can always pause, go back and rewatch this. And you are responsible for this proof. You need to know this. You need to know all of this. Okay, all of this stuff I'm holding you responsible for. The proof of part 2 involves a little trick, so you're not going to be responsible for this. But it's going to be a similar proof, so let's consider the quantity. Now it's going to be AC minus BD, because we're trying to show that AC is congruent to BD mod M. Okay, so I write AC minus BD, and then I'm stuck, right? I don't have an A minus B, I don't have a C minus D, I'm stuck. So what I'm going to do is I'm going to do a little trick here. I'm going to write AC minus BC plus BC minus BD. And this is kind of a dirty trick, right? I've just added and subtracted the same quantity, which I can do. That's basically adding 0. But in so doing, now I can factor a C out of the first pair and factor a B out of the second pair, and I'll get back a hold of these quantities like I wanted. So this is equal to C times A minus B plus B times C minus D. And this now is equal to what? C times, well, A minus B was Km, plus B times, well, C minus D is Lm. And with this put all together, I end up with, well, I can factor out an M, and I have CK plus BL. All right? And as before, surprise, surprise, this is an integer, which means M divides the quantity this, which means M divides the quantity this, which means M divides the quantity this, which means M divides the quantity AC minus BD. If M divides the quantity AC minus BD, now we're really happy. This means AC is congruent to BD mod M. Okay, and that's the end of the proof, but I'll go back through it just a little bit. The tricky part here, at least, and maybe this is straightforward to you, but for me the tricky part isn't like the main idea, because the main idea is the same. It's, unfold these definitions. Unfold these definitions to get these representations of A minus B and C minus D. To me, that's not so challenging. Okay, and I also think it's not so challenging to see that if I need to show AC is congruent to BD, then I need to consider AC minus BD. What is challenging to me is this thing right here, this remembering to add and subtract some quantity. Now, after you've been doing mathematics for a while, maybe by the time you graduate college, such tricks might not seem so fascinating or surprising. So you might see things like that and not be so surprised. But I think at this level in your sort of mathematical journey, expecting you to just remember to add and subtract a piece is a little bit beyond what I really want to, what I really want you to focus on in a discrete math course. So we consider the quantity AC minus BD. Through this little trickery, we end up able to get our hands on A minus B and C minus D. We rewrite these as factors of M, like we found up here, and we get CKM plus BLM. We can factor the M out. We get M times an integer, and that's how we sort of finish up. Now, if you're curious, where did BC come from? I think it's not so far out there, because I want somehow to relate this quantity to this quantity. And I know something about A minus B, and I know something about C minus D. So if there was a way to sort of get this C with this D and get this A with this B, it'd be great. And one way to do that is to kind of, pull off half of each. So I sort of did something with the C and the B. Now, I can't just subtract something unless I add it back in, and BC just happens to be a quantity that works. I think you could also run the exact same type of trick by adding and subtracting AD, and it would also work. Okay, so we're almost done now. Last thing I want to do is I want to define Z mod M. So Z mod M is a set 0, 1, 2, 3, ... all the way up to M minus 1. And this is for any m natural, we can define this set. So for example, z mod 5 is just going to be 0, 1, 2, 3, 4. Okay, so for any natural number, I can define z sub n, right? Now we've got plus sub m and times sub m, as you'll recall. So if I have a plus sub m b, that's just equal to n, where n is congruent to a plus b mod m, and n is an element of z sub m. And this is same for times sub m. So a times sub m b is equal to n, where n is congruent to ab mod m, and n is an element of z sub m. So let's do just a couple of examples of this. Actually, I think I'm going to move this over to the next page. Let's do just a couple of quick examples of this so you can see it here. Let's do 5 plus sub 7, 6. So 5 plus sub 7, 6 is going to mean, well, I add 5 to 6, so I get 5 plus 6 is 11. And what is 11 congruent to in mod 7? That's going to be congruent to 4 mod 7. So the answer is 4. Let's do another example. Let's do 31 times 276, times sub 2, 276. So all this does, I could multiply out 31 and 276. It would take a while, but what I'm going to do instead is I'm going to say, well, 31 is congruent to 1 mod 2, and 276 is congruent to 2 mod, or is congruent to 0 mod 2. So this thing is equal to 0. All right, because I'm working mod 2. So that's what this little number down at the bottom does. Let's do another couple of examples. Hopefully it'll make a little bit more sense. So basically, if you've seen the programming concept before, this is just the same as 5 plus 6 percent sign 7. If you've seen this before, this is the same as 31 times, in computer programming languages, is frequently an asterisk, times 276, and then percent sign 2. That's what this one would be in sort of computer language. Let's do another quick one. Let's do 4 plus sub 10, 299. Okay, well this is equal to, how do I do this? I could either add these and then reduce mod 10, or I can reduce mod, like I did with this one, I can reduce mod 10 first. So this is going to be congruent to 4 plus 9 mod 10. And so this is 13 mod 10. But we notice 13 is not an element of Z10. It's not a number between 0 and 9. So this is equal to 3, and 3 is an element of Z10. Right, so that would be our final answer here. Let's do one more. Let's do 5 times sub 7, 10. And this time I'm going to go ahead and multiply it out and look for whatever 50 is mod 7. So 50 is congruent to what mod 7? Well, it's 1 more than 49. So this is congruent to 1 mod 7, because 49 is a multiple of 7. So the answer is 1. I hope this makes sense. I would say, run through these last few examples a couple more times to make sure that they're clear, and have a